Imagine waking up tomorrow to discover that gravity has stopped working. Not everywhere, not permanently, just for 1 second. For 1 second, planets drift from their orbits, stars lose their structure, galaxies begin to unravel. The moon no longer knows how to circle Earth. Oceans rise from their basins. The entire architecture of the cosmos starts falling apart. Then, 1 second later, gravity returns. The universe survives. But physicists would be left asking a terrifying question. Why did gravity come back? What forced it to return? What guarantees that gravity will exist tomorrow? We often speak about the laws of physics as if they are written into reality itself. Gravity attracts. Light travels at a fixed speed. Energy is conserved. Every atom follows precise mathematical rules. But have you ever stopped and asked a deeper question? Why are there laws at all? Not what the laws are, not how they work, but why they exist. Because the universe could have been chaos. Nothing in logic demands the existence of gravity. Nothing in mathematics requires electrons to exist. Nothing forces time to move forward. Nothing guarantees that the speed of light must have exactly the value it does. Yet somehow, reality behaves according to an astonishing set of rules. The deeper scientists look, the more mysterious this becomes. Every successful theory in physics eventually reaches a point where it simply says, "This is the law." Newton described gravity. Einstein explained gravity more deeply. Modern physics describes gravity using geometry. But eventually, every explanation reaches a wall. Why should spacetime have those properties? Why should geometry control motion? Why should there be a spacetime at all? The question remains, why do physical laws exist? And this question may be one of the deepest questions ever asked by the human mind.
Because if we can understand why physical laws exist, we might finally understand why reality exists. To appreciate how strange this mystery is, we need to begin with something so familiar that we almost never notice it. Patterns. Every scientific law begins as a pattern. Thousands of years ago, humans noticed that the sun rises every morning. The seasons repeat. Objects fall downward. Fire burns. Water flows. At first, these observations seemed unrelated. But gradually, a remarkable realization emerged. Nature is predictable. The universe behaves in regular ways. Ancient civilizations built calendars because celestial motions followed repeating patterns. Farmers planted crops because seasons returned reliably. Navigators crossed oceans because stars followed predictable paths. Long before physics existed, humanity discovered something extraordinary. Reality appears organized. This may sound obvious today, but imagine a universe without regularity. Imagine a universe where gravity changes every Tuesday. Imagine a universe where atoms sometimes behave differently for no reason. Imagine a universe where mathematics works today but fails tomorrow. Science would be impossible. Prediction would be impossible.
Memory itself would become unreliable because the rules governing matter could change without warning. The very existence of intelligence may require stable laws. This is something many people never realize. Every thought occurring inside your brain depends upon physical regularities. Neurons obey electromagnetism. Atoms obey quantum mechanics. Chemistry obeys precise mathematical relationships.
Your ability to ask questions depends on laws already existing. Which makes our question even stranger. How can creatures created by physical laws explain the existence of physical laws? The first great attempt came from Isaac Newton. In the 17th century, Newton accomplished something astonishing. He discovered that the same force causing an apple to fall also controls the motion of the moon. One equation unified Earth and heaven. For the first time in history, the universe appeared to operate according to universal mathematical rules. Newton's law of gravitation worked brilliantly. It predicted planetary motion with incredible accuracy. It explained tides. It explained comets. It explained celestial mechanics. Many believed the mystery had been solved, but Newton himself recognized a deeper problem. His equation described how gravity behaves. It did not explain why gravity exists. In fact, Newton was deeply uncomfortable with this issue. He famously admitted that he could not explain how gravity acts across empty space. The mathematics worked. The mechanism remained mysterious. This distinction is crucial. Physics often tells us how. Much more rarely does it tell us why. As centuries passed, scientists discovered more laws. Maxwell unified electricity and magnetism. Thermodynamics revealed laws governing heat and energy. Quantum mechanics uncovered rules controlling atoms. Each discovery increased our understanding, yet each discovery also deepened the mystery, because every new law raised another question. Why that law instead of another? Why should electric charges exist? Why should energy be conserved? Why should quantum particles obey probabilities? The universe seemed increasingly elegant, but elegance is not an explanation. Then, in the early 20th century, a revolution arrived. A patent clerk named Albert Einstein looked at Newton's gravity and realized something remarkable. Perhaps gravity is not a force. Perhaps gravity is geometry. Einstein proposed that matter bends spacetime itself. Planets orbit stars because they follow paths through curved geometry. Gravity became a consequence of spacetime structure. It was one of the greatest intellectual achievements in human history. For the first time, a law appeared to emerge from something deeper. Gravity was no longer a mysterious force reaching across empty space. Instead, gravity became a manifestation of geometry. Many physicists hoped this process would continue forever. Perhaps every law could eventually be explained by a deeper law. Then deeper still. Then deeper again. But an uncomfortable question remained hidden beneath the progress. What explains the deepest law? Imagine a chain hanging from the ceiling. Each link supports the one below it. You can explain the position of one link by referring to the link above, and that link by referring to another. Eventually, you reach the top. What holds the top link? The search for physical laws may face a similar problem. Every explanation seems to require another explanation. Every law seems to rest upon deeper principles. But eventually, physics may reach bedrock. And when it does, what explains the bedrock itself? This dilemma has haunted some of the greatest physicists who ever lived.
Einstein spent decades searching for a unified theory. He hoped all physical laws would emerge from a single mathematical framework. Others continued the search after him. Today, scientists pursue theories capable of unifying gravity and quantum mechanics. Some believe a final theory exists. Others are not so sure. Because even if a final theory exists, a profound question remains. Why that theory? Why should reality obey those equations? Why not different equations? Why not no equations at all? At this point, our journey enters territory where physics begins touching philosophy. But this is not a weakness. It is unavoidable. When we ask why physical laws exist, we are asking about the foundations of reality itself. And foundations do not surrender their secrets easily. The deeper we dig, the stranger reality becomes. Because modern physics has revealed something even more astonishing than physical laws. It has revealed that many laws appear astonishingly fine-tuned. The strength of gravity, the masses of elementary particles, the strength of electromagnetism, the value of the cosmological constant. Tiny changes in these numbers could make stars impossible, galaxies impossible, chemistry impossible, life impossible. The universe appears balanced upon a razor's edge, and that raises another question. Are physical laws inevitable, or are they accidental? Scientists have spent decades exploring this mystery. Some believe the laws could not have been different. Others suspect countless alternative universes may exist, each with different laws. And if that possibility is true, then our universe may be only one member of a much larger cosmic landscape, a possibility so vast that it transforms our understanding of existence itself. To understand how physicists arrived at such extraordinary ideas, we must first examine something even more fundamental: the surprising relationship between mathematics and reality. Because before we can ask why physical laws exist, we must ask another mystery. Why does mathematics describe them so perfectly? This question sounds simple. In reality, it may be even stranger than the existence of physical laws themselves. Think about what mathematics actually is. Numbers do not exist physically. You cannot pick up the number 3. You cannot hold a triangle in your hand. You cannot travel to a location where algebra lives. Mathematics appears to be an abstract creation of the mind. Yet somehow, these abstract ideas describe reality with astonishing precision. Centuries before telescopes revealed distant planets, mathematics predicted their existence.
Long before physicists discovered antimatter, equations implied it should exist. Before scientists observed gravitational waves, mathematics suggested they were possible. Again and again, reality behaves as though it is reading a mathematical script. This mystery fascinated physicist Eugene Wigner. In 1960, he published a famous paper called The Unreasonable Effectiveness of Mathematics in the Natural Surface. Wigner argued that mathematics works far better than anyone has a right to expect. And he was correct. Consider something extraordinary. When James Clerk Maxwell wrote down equations describing electricity and magnetism, he noticed a surprising result. The equations predicted waves moving through space. When he calculated their speed, he obtained a value already known from experiments: the speed of light. Light itself emerged from mathematics. Scientists were not studying light, they were studying electricity. Yet hidden inside the equations was a fundamental feature of reality. This keeps happening. The mathematics often knows more than the scientists using it. It is almost as if reality and mathematics are deeply connected beneath the surface. But why? Some physicists believe mathematics is merely a human language. Others suspect mathematics exists independently of human minds. If the second possibility is true, the implications are staggering. Perhaps physical laws exist because reality itself is mathematical. Perhaps the universe is not described by mathematics. Perhaps the universe is mathematics. This idea has been explored by physicists such as Max Tegmark. His proposal is radical. According to the mathematical universe hypothesis, every consistent mathematical structure exists physically. our universe would simply be one mathematical structure among countless others. Most physicists remain skeptical. Yet the proposal highlights an important point. The deeper science progresses, the more reality seems intertwined with mathematics. And this leads us to another remarkable discovery. Many physical laws appear to emerge from something even more fundamental than forces: symmetry. The word symmetry usually brings to mind shapes or patterns: a snowflake, a butterfly, a crystal. But in modern physics, symmetry means something far deeper. A symmetry exists when something remains unchanged under a transformation. Imagine standing inside a laboratory. You perform an experiment. Now imagine performing exactly the same experiment tomorrow. You expect the result to be identical. This expectation reflects a symmetry. The laws of physics do not appear to care whether it is Monday or Tuesday. Now imagine moving the laboratory to another city. The laws remain unchanged. Again, symmetry. Physics does not appear to care where the experiment occurs. The implications of this idea became revolutionary through the work of mathematician Emmy Noether. In 1915, she discovered one of the most profound relationships in all of science. Noether showed that symmetries generate conservation laws. This was not merely a useful observation. It was a deep mathematical truth. If the laws of physics remain unchanged through time, energy is conserved. If the laws remain unchanged through space, momentum is conserved. If the laws remain unchanged through rotation, angular momentum is conserved. Suddenly, conservation laws were no longer arbitrary rules. They emerged naturally from symmetry. This was a breathtaking revelation.
Scientists had found a deeper layer beneath the laws. Imagine uncovering ancient ruins. At first, you see buildings. Then you discover foundations beneath the buildings. Noether revealed some of the foundations beneath physical law. And yet, the mystery survived. Why do these symmetries exist? Why should reality possess such elegant structure? Why should nature prefer symmetry over chaos? Every answer seemed to reveal a deeper question. This pattern appears repeatedly throughout physics. Scientists discover a law. Then they discover a principle beneath the law. Then a principle beneath that principle. Each layer seems more fundamental than the one before, and each layer raises new mysteries. By the middle of the 20th century, physicists had uncovered another astonishing fact. Matter itself appears to be governed by invisible symmetries. The particles making up reality are not random. They fit into mathematical patterns so precise that many researchers initially thought they must be accidental. Yet experiment after experiment confirmed the structure. Electrons, quarks, neutrinos, photons, all seemed connected through hidden mathematical relationships. Eventually, these discoveries produced one of the most successful scientific theories ever created: the Standard Model of particle physics. Its predictions have been confirmed repeatedly with astonishing accuracy. In some cases, agreement between theory and experiment reaches more than 10 decimal places. Such precision is almost unimaginable. If physical laws were a machine, the Standard Model would be one of the most accurate machines humanity has ever discovered. Yet, there is something unsettling about it. The Standard Model works, but nobody knows why it has exactly the structure it does. The theory contains numerous numerical constants: particle masses, force strengths, mixing angles, values that must simply be inserted. The equations describe reality beautifully, but they do not explain why these numbers exist. It is similar to finding an incredibly sophisticated computer. You can study its operation, you can understand its software, you can predict its behavior, yet you still do not know who chose the settings or why those settings were selected. And that mystery becomes even more dramatic when we examine the universe itself. because many of these constants appear astonishingly special. Imagine changing the strength of gravity slightly. Stars could burn too quickly or never ignite. Increase the strength of the strong nuclear force. Chemistry changes dramatically. Decrease it, atomic nuclei become unstable. Small modifications can produce universes radically different from our own. Some may contain no stars. Some may contain no complex chemistry. Some may collapse moments after forming. Others may expand too rapidly for galaxies to emerge. Physicists call this fine-tuning, and whether fine-tuning is real remains one of the most controversial questions in modern science.
Some researchers believe the apparent fine-tuning points toward deeper, undiscovered laws. Others believe it may be evidence for multiple universes. Others argue we simply lack sufficient understanding to draw conclusions. Yet everyone agrees on one thing. The question is extraordinary. Because if physical laws could have been different, then we must ask why they are not. And if they could not have been different, then we must ask what necessity forces them to be exactly as they are. Either possibility leads to profound consequences. Notice what has happened to our investigation. We began with gravity, then laws, then mathematics, then symmetry, then conservation principles, then particle physics. Each step has carried us deeper beneath the surface of reality. And now we are approaching one of the most important turning points in modern physics, a realization that completely transformed how scientists think about the universe. The realization that particles themselves may not be fundamental at all.
Because according to modern quantum field theory, the universe may be built from something even deeper than matter: fields. So now we move from symmetry and the standard model into something even more unsettling. Modern physics reaches a point where particles stop being the foundation of reality. Instead, what we call particles are actually excitations of invisible fields that fill all of space. This idea comes from quantum field theory. In this framework, space is not empty. Even vacuum is not nothing. It is more like an ocean of fields that are always present everywhere. The electron is not a tiny ball flying through space. It is a ripple in the electron field. A photon is a ripple in the electromagnetic field. Quarks are ripples in quark fields. So what we call matter is just patterns in underlying fields. This already changes the picture of reality dramatically. But now comes the deeper question. Why do these fields exist at all? And why do they follow the rules they do? Because quantum field theory doesn't eliminate physical laws. It just pushes them deeper. Now, instead of asking, why do particles behave this way? We ask, why do fields behave this way? And now we hit something important. Even the vacuum is not truly empty. Due to quantum mechanics, the vacuum constantly fluctuates. Particles briefly appear and disappear. Energy levels constantly shift.
This is not speculation. It has been measured indirectly in effects like the Casimir effect, where two metal plates in a vacuum experience a tiny force because of quantum vacuum fluctuations. So even nothing in physics is something. But still, we are left with the same problem. Why does even the vacuum obey mathematical rules? At this point, modern physics starts to feel like it is describing not objects, but relationships. Not things, but structures. And this leads some physicists to a radical idea. Maybe physical laws are not rules imposed on reality. Maybe they are just descriptions of deeper structures that must exist for consistency. In other words, maybe laws are not chosen. Maybe they are unavoidable. But then we face a tension, because the standard model and quantum field theory are extremely successful, yet they contain arbitrary-looking constants.
This is where modern theoretical physics becomes unsettled. Physicists start asking, could there be a deeper theory where even these constants are not arbitrary? This is part of what drives attempts like string theory and other unification programs. In string theory, for example, particles are not point-like objects at all. They are tiny vibrating strings. Different vibrations correspond to different particles. But here's the key idea. The laws themselves may emerge from the geometry of these vibrations. However, string theory also opens another problem. It doesn't give a single unique universe. It may allow a vast number of possible solutions, sometimes estimated as something like 10 to the 500th possible vacuum states. This leads to a controversial idea in physics.
Maybe the laws we observe are not uniquely determined. Maybe they are just one possibility among many. This connects to the idea of a multiverse, where different regions of reality could have different physical laws. If that were true, then our question shifts again. We would no longer ask, why do laws exist? But instead, why do we live in this particular set of laws? This is where the anthropic principle enters the discussion. It suggests that we observe these laws because only these kinds of laws allow observers like us to exist. It sounds almost circular, but it is taken seriously in some areas of cosmology, especially when discussing fine-tuning of constants, like the cosmological constant, the strength of gravity, particle mass ratios. Even tiny changes in these values would prevent galaxies, stars, or chemistry from forming. But there is still something deeply unsatisfying about this explanation, because it doesn't fully answer why laws exist. It just reframes the question statistically. So now physics stands at a strange edge. On one side, we have extremely successful mathematical theories describing reality with extraordinary precision. On the other side, we have no explanation for why those mathematical structures exist in the first place. And this is where things become even more philosophical, but still grounded in real scientific discussion. Some physicists begin to suspect that laws of physics might not be fundamental at all. Instead, they might be emergent, like temperature. Temperature is not a fundamental property of a single molecule. It emerges from the motion of many particles together. So the question becomes, could physical laws themselves emerge from something deeper? This is where ideas like information theory, quantum computation, holographic principle from black hole physics, and spacetime emergence start becoming relevant. In modern theoretical physics, there are serious proposals that spacetime itself might emerge from quantum entanglement, that space is not fundamental, that geometry is built from information relationships. If that is true, then physical laws might not be written rules of reality. They might be consequences of how information can exist consistently. But even here, we have not escaped the original question, because we can always ask, why does information obey those constraints? Why those mathematical rules and not others? So the deeper we go, the more the question transforms, but never disappears. We moved from gravity to laws, to mathematics, to symmetry, to fields, to information. And at every step, we found deeper structure, but never a final explanation for why structure exists at all. And this is where modern physics quietly reaches one of its most honest positions.
At the deepest level we currently understand, physics does not explain why physical laws exist. It only describes what those laws are, and the rest becomes an open frontier. Now we are ready to go further into one of the most mysterious ideas in all of physics. The possibility that the universe, at the deepest level we currently understand, physics does not explain why physical laws exist. It only describes what those laws are, and the rest becomes an open frontier. Now we are ready to go further into one of the most mysterious ideas in all of physics: the possibility that the universe is not just described by laws, but that laws themselves might be a kind of emergent language of reality. When physicists study gravity at the deepest level, especially near black holes and the early universe, something strange appears. The smooth spacetime we experience begins to break down. Einstein's general relativity describes gravity as curvature of spacetime, but quantum physics refuses to let spacetime stay smooth. At extremely small scales, the Planck scale, spacetime may become irregular, fluctuating, almost grainy. Not space as a continuous fabric, but something far more abstract underneath it. This is where quantum gravity research begins. And there is a disturbing gap in physics here. We have two incredibly successful theories: general relativity, gravity, stars, galaxies; quantum mechanics, atoms, particles, forces, but they don't fit together cleanly. When combined, the mathematics breaks down. So physicists suspect something deeper must exist, something that produces both spacetime and quantum fields as approximations. One of the leading ideas is that spacetime itself might not be fundamental. Instead, it could emerge from quantum entanglement. This idea is supported in part by research connected to black holes and holography. In black hole physics, something surprising was discovered. The information content of a volume of space seems to scale with its surface area, not its volume. This is known as the holographic principle, strongly motivated by work on black hole thermodynamics. It suggests that the entire 3D universe might be describable by information encoded on a 2D boundary. That alone changes everything, because it means what we experience as space might be a projection of deeper information rules, not unlike a hologram. And if space is emergent, then all physical laws that depend on space must also be emergent. That includes gravity, motion, even causality. But this raises a deeper question. If space-time is not fundamental, what is? One answer some physicists explore is quantum information. In this view, the most basic thing in the universe is not matter, not energy, not even space-time, but relationships between bits of information. Entanglement becomes the key ingredient. When two quantum systems are entangled, they are no longer independent. Their states are linked, even across distance. Some modern research suggests that the geometry of spacetime might actually be constructed from patterns of entanglement. Roughly speaking, more entanglement, closer geometry; less entanglement, farther geometry. So distance itself may be derived from information structure. This idea appears in approaches related to quantum gravity and black hole theory, and is actively studied in theoretical physics. But even if this is correct, we still have not answered the main question. We have only shifted it again. Because now we ask, why does information behave in this structured way? Why entanglement? Why these rules of quantum mechanics instead of others? At this point, physics reaches a strange intellectual boundary. We can describe reality with extreme precision. We can predict particle behavior to incredible accuracy. We can build entire cosmological models that match observations. But the origin of the rules themselves remains unexplained. And this is where the question becomes almost unavoidable. Are physical laws discovered or invented? If laws are discovered, then they exist independently of the universe. If they are invented, then something must be doing the inventing. But what? Some physicists take a mathematical realist position. They argue that mathematical structures exist independently, and physical reality is one of them. Others argue the opposite, that laws are simply effective descriptions of patterns we observe, not deeper truths. But neither view fully resolves the mystery, because both still assume something exists that behaves lawfully. Even randomness in quantum mechanics is not lawless. It is statistically structured. Even probability follows precise equations. So even chance is governed. And that is what makes this question so powerful. No matter how deep we go, reality never becomes completely structureless. Instead, it becomes more structured the deeper we look. This is one of the most surprising discoveries in all of science. We expected that digging deeper into reality would lead to simplicity. Instead, we found layers of abstraction. Particles, fields, spacetime, entanglement, information, mathematical consistency. Each layer removes familiar intuition, but each layer adds deeper order. And now we arrive at a very modern perspective in theoretical physics. Maybe the reason physical laws exist is because only structured systems can be self-consistent. In other words, reality might not choose laws. Instead, only certain logical structures can exist without contradiction. This idea appears in different forms across modern research, including approaches to quantum gravity, computational universe models, and mathematical physics. But it is still not a final answer. It is only a direction. And that brings us back to where we started. We asked, why do physical laws exist? And after everything we have explored, from gravity to quantum fields to space-time emergence, the answer we currently have is surprisingly simple and deeply unsettling. We do not know. We can describe the laws. We can unify them. We can derive them from deeper frameworks, but the existence of the framework itself remains unexplained. And that is where the real frontier begins. Because the next step in physics may not be finding a new particle, or a new force, or even a new equation. It may be understanding why equations exist at all. What if physical laws are not fixed at all? In almost all of physics, we assume laws are permanent. Gravity doesn't decide to change tomorrow. Electromagnetism doesn't rewrite itself. The equations are assumed to be eternal. But this assumption is based on observation inside our cosmic region, not a proven necessity. So some physicists have asked a radical question. What if laws themselves can evolve? Not randomly, but through some deeper meta-law, a rule that governs how laws behave. This idea appears in different forms in theoretical research, especially in cosmology and complexity science. One motivation comes from the early universe. Right after the Big Bang, the universe was extremely hot, dense, and unstable. In such extreme conditions, we suspect that familiar physical descriptions may not fully apply. So it is not unreasonable to ask, did the laws we see today settle into their current form over time? Or were they always fixed? We don't have direct evidence either way, but we do know something interesting. The constants of nature appear extremely special. If you slightly change them, the universe becomes unrecognizable. This has led some researchers to imagine scenarios where universes are not static systems, but evolving ones. One famous speculative idea connected to this line of thinking is cosmological natural selection, proposed by physicist Lee Smolin. In this idea, new universes might be born inside black holes, and each new universe could inherit slightly modified physical constants. Over time,
universes that produce more black holes would become more common. This creates a kind of evolutionary process at the level of universes, not biology, but cosmology shaped by selection. The laws are not chosen, they are filtered. This is not mainstream accepted physics, but it is taken seriously enough to be discussed in theoretical cosmology. And it shows something important. Once you allow the possibility that laws are not fixed, the question of why these laws transforms completely. It becomes a question of history, not design. But even this idea does not escape the deeper mystery. Because even in a system where laws evolve, we must still ask, what governs that evolution? What defines the space of possible laws? Why that meta rule instead of another? So the hierarchy continues. Now we are no longer asking about particles or forces. We are asking about rules that generate rules. And this brings us to another major idea in modern theoretical physics: the universe as a computational or self-processing system. In this view, reality is not a static structure. It is a process, a continuous computation unfolding moment by moment. Every interaction between particles is like an update rule. Every quantum event is like an information transformation theory and digital physics. But again, we must be careful. This is not saying the universe is a computer in a literal engineering sense. It is saying something deeper, that the universe might be best described as a system where information evolves according to consistent transformation rules. And if that is true, then physical laws are not external rules imposed on reality. They are simply the internal logic of the process itself. But even then, the question remains open. Why does any such process exist? Why is there something that evolves rather than nothing at all? At this stage, physics begins to overlap heavily with philosophy of existence. But it is important to notice something very precise here. This is not a failure of science. It is what happens when science reaches its boundary of explanation. Because science is extremely powerful at answering how systems behave, how interactions occur, how predictions can be made. But science may not be designed to answer why there is a system at all, why rules exist instead of nothing, why mathematics maps onto reality. And yet, the attempt to push into that boundary has produced some of the most profound ideas in human history. We now have a picture of reality that looks like this. At the surface, matter, forces, particles. Deeper, fields and quantum interaction structure. Deeper still, space-time geometry. Deeper still, entanglement and information structure. Deeper still, mathematical consistency conditions. And beyond that, something we cannot yet describe. And the most honest position modern physics can take is this: we have not reached the final explanation. We have only uncovered deeper layers of structure. Each layer feels more fundamental. Each layer feels more necessary. But none of them explain why the chain exists in the first place. And this brings us to the final conceptual tension at the heart of everything we've discussed. If the universe is purely mathematical, then mathematics itself must exist independently. If the universe is physical, then physical law must be explained by something physical. If the universe is informational, then information rules must be grounded in something deeper. Every possible foundation pushes the question one step back. And so the question, why do physical laws exist, may not have a simple answer. Not because it is meaningless,
but because it may be pointing at the limit of explanation itself. And so, after thousands of years of observation, centuries of mathematics, and generations of scientific discovery, we arrive at a surprising truth. We know more about the universe than any civilization before us. We know that stars are powered by nuclear fusion. We know that galaxies drift through expanding space. We know that matter is built from quantum fields. We know that time and space are woven together into a single fabric. And yet, beneath all of this knowledge, one question remains untouched. Why are there laws at all? Why should reality obey mathematics? Why should the universe be understandable? Why should existence possess order instead of chaos? Perhaps future discoveries will reveal a deeper theory, a framework from which gravity, quantum mechanics, spacetime, and every physical constant emerge naturally. Or perhaps every answer will simply uncover another layer.
Another question waiting in the dark. Because throughout this journey, one pattern has appeared again and again. Every time humanity thought it had reached the foundation of reality, a deeper foundation appeared underneath. The atom was not fundamental. Particles were not fundamental. Fields may not be fundamental. Even space-time itself may not be fundamental. The deeper we look, the more reality seems less like a collection of objects and more like a network of hidden relationships governed by an astonishing mathematical order. And maybe that is the greatest mystery of all. Not that the universe is vast. Not that it is ancient. Not that it contains billions of galaxies. But that it is comprehensible. That a small collection of atoms on a tiny planet can discover equations that describe black holes, predict unseen particles, and reveal events that happened billions of years before humans existed. Somehow, the universe allows itself to be understood. And perhaps that is the closest thing we currently have to an answer. Physical laws may not simply be rules written into reality. They may be the very reason reality can exist, persist, and make sense at all. For now, the origin of those laws remains unknown. But every equation we write, every experiment we perform, and every mystery we uncover brings us one step closer to understanding the deepest question physics has ever asked. Not how the universe works, but why there is a universe that works in the first place.